All right. So let us talk about inclusion exclusion principle, right? So this is bit mathematical, but you have also studied this in school while studying set theory, right? So suppose you have two sets, one set is A and another set is B, and let's say these sets are disjoint sets, and you want to compute A union B, right? So let's say A is those people who like apple, B is the number of people who like mango, so they form a different set. And if I compute A union B, right, then it is given by A plus B, right, where this notation represents the cardinality of the set, right, the number of elements in that set, right. So if there are 10 people in set A who like mango and there are 20 people in set B who like apple, then the number of people who like apple or mango is going to be 20, right. So let us make it slightly difficult. Let's say there are people who also like both apple and mango, right, so which means there is some overlapping between the sets A and B, right. So in that case, the formula that we are going to use is, if I want to compute A union B, right, and the cardinality of this set, right, so it is going to be cardinality of A plus the cardinality of B minus what is common, right, because we are counting this part which is common twice, right, so we just subtract this part because it has been counted twice, right. So this is A intersection B, right. So this is what the inclusion exclusion principle is all about, right. So this formula we have written is for two elements, but you can also have this formula has been written for two sets, but there can be more sets. So let us say you have three number of sets. One set is A, one set is B, and one set is C, and you want to find out the union of all these sets, right. So A union B union C, it can be written as A plus B plus C minus A intersection B minus B intersection C minus C intersection A plus this part, which is A intersection B intersection C. All right. So this is, again, this is written when we have three sets, but you can also have more number of sets, right. The reason why I'm doing this is because this concept is going to be used in competitive programming, right, so you should understand this very carefully. Similarly, you can have problems in which you need to combine more number of sets, right. So let's say you want to find out A union B union C union D, right. Then the formula would look something like this: A plus B plus C plus D minus, you are going to combine sets in pairs of two, so A intersection B, B intersection C, C intersection D, and so on, right. So this goes on, and then you're going to add, let's say, uh, you're going to combine sets in triplets, right. Then you will add all those terms in which three sets are occurring, so you will add A intersection B intersection C plus A intersection B intersection D, right, and so on. And then you are going to subtract all those terms in which the set is occurring four times. The number of sets they are occurring are four, right. So if you observe this general trend, right, so what is the general trend? The trend is like this: if you're combining only odd number of terms, odd number of sets, then the sign would be positive. If you are combining even number of terms, like in this case, the sign would be negative. If you are again combining three sets, then the sign would be positive. You are combining four sets, the sign would be negative, right. So effectively what you need to do, you need to generate all subsets, generate all subsets of this set, and if a subset has odd number of elements, you're going to add the answer for that, and if a subset is going to have even number of elements, you're going to subtract the answer for that, right. Okay, so let's have a look at a problem, right. So uh, the problem is like this. You want to find out how many numbers are there which are less than 1000, right? How many numbers are there such that they are less than 1000 and they are divisible by 2 or 2, 3 and 5, right? So how many numbers less than 1000 are there such that they are divisible by 2, 3 and 5, right? So this is the problem I want to solve. So let us see how we can approach this problem, and uh, we are going to use the principle we have learned, right? So first of all, I need to find out how many numbers are there which are less than 1000 and they are divisible by 2, right? So effectively I want to find out the numbers in the range 1 to 999 such that they are divisible by 2, right? So let us find the number of numbers in which are divisible by 2, right? So this would be given by 999 divided by 2 and you take a lower bound, right? So this comes out to be 441 9 numbers, right? So similarly I need to find out the number of numbers which are divisible by 3. So if you want to find, if you have a number n and you want to find the number of numbers which are divisible by m below n, right? So it is given by floor of this value. You can clearly verify, right? If you have n equals to 1000 and you want to find out how many numbers are divisible by 2, right? So it is going to be this is going to be 499, right? Yeah. And so this is going to be 500, right? Okay. So the number of numbers which are divisible by 3, it would be given by floor of 999 divided by 3, which is equal to 333, right? And I also need to find out those numbers which are divisible by 5, so it is going to be floor of 999 divided by 5. So this comes out to be 199, right? Okay, so now what is the problem statement? The problem says I want to find out all those numbers which are divisible by 2 or 3 or 5. So this is effectively what I need to find out, right? So this can be written as the cardinality of set 2 plus the cardinality of 3 plus cardinality of 5 minus cardinality of 2 intersection 3 minus 2 intersection 5 minus 3 intersection 5 plus all those numbers which are divisible by all three of them, right? So effectively this is what we need to figure out, right? So these terms you already know how many numbers are divisible by 2, 3 and 5. So this basically means all those numbers which are divisible by both 2 and 3, right? So let us find out all those numbers which are divisible by 2 and 3. So this would be given by 999 divided by 2 and divided by 3. Basically I want to find out all those numbers which are multiples of 6, right? So this is what it is going to be, right? So 2 into 3, which is 6, and this comes out to be around 166, right? And similarly you need to find out all those numbers which are divisible by 2 and 5. So you can do floor of 999 divided by 2 into 5, all multiples of 10. So it is going to be 99. And similarly you need to find out 3 and 5. It is going to be 999 divided by 15, 3 into 5. So this comes out to be around 33. Oh, sorry. This comes out to be around 66, right? And finally, you need to find out all those numbers which are divisible by 2, 3 and 5 all, right? So it would be given by 999 divided by 2, 3 and 5. So 15 into 2, 30, and 999 divided by 30 is equal to 33, right? So now you can clearly figure out what it is going to be. So let us add all these terms. So this term is 499 plus 333 plus 199 minus 166 minus 99 minus 66, and this term is 33, right? So it comes out to be 733, right? So there are 733 integers up to 1000 which have at least 2, 3 or 5 as the divisor, and this also includes 2, 3 and 5, right? So they have either 2, 3 or 5 as the divisor, right? So these many numbers are there, right? Okay, so now I will talk about how to implement the same thing, right? So if you uh, have a array of, let's say, numbers, for which you want to find out how many numbers are there for some value less than n, which are divisible by these number, right? So first thing is you need to generate all subsets, right? So all subsets of 2 3 5 are 2 3 5 2 and 3 3 and 5 and 2 3 5, right? So we need to generate all the subsets, and then we will see if the subset contains even elements or odd elements. If the elements are even, right, then we are going to take their product and divide our n with that, and if the number of elements are even, we will subtract that value, right, that we have already seen, right? Like here, right? So if the number of elements are even, we are going to subtract that value, and if the number of elements are odd, then we are going to add that value, right? And how do you compute subsets? So for computing subsets, I'm going to use bit masking, right? So I will talk about how to use bit masking. For example, if you have a set of elements a, b and c, right? So this is clearly going to have 2 raised to the power 3 subsets, right? Okay, but I just need all those subsets which have at least one element. So I will start, I will just number from 1 to 2 raised to the power n minus 1. So it is basically 7, right? And I'm going to write their binary. So 1 is like this, 2 is like this, 3 is like this, and you have 4, you have 5, you have 6, and you have 7, right? So if you clearly see, right, and if you take a particular number from here and corresponding uh, character from here, and if you choose numbers according to the set bit, right? For example, if you have a 1 here, then if you will choose c from here, right? So you will get c as a subset. You have 1 here, you will choose b, you will get b. You have 1 here, you will get b and c. You have 1, you will get a. From here you will get ac, and here from here you will get ab, and from here you will get abc, right? So this is what all subsets are going to do, right? So similarly, for computing these numbers, I'm going to use bit masking. So I will basically iterate over range from 1 to 2 raised to the power n minus 1. Then I'm going to generate this number, and then I'm going to extract bits and take that number, right? So what I need to do, I need to take a product of these numbers, right? So that I can compute n divided by the product. Okay, and then I will see if the number of terms in it are odd or even. So if the number of terms are, like in this case, are odd, so this n divided by product of the numbers abc, this will be added to my answer, right? If the number of terms are even, then this would be subtracted from my answer, right? So this is what I am going to do in this. If you need to implement this kind of a thing, right? And all these numbers should be prime, right? And now let us go through the problem. Okay, so the problem is on Coding Blocks Online, and it is also on Hackerblocks, right? So let us see what the question is saying, right? So it says, after the release of Avengers, Iron Man and Thor got into fight, and Iron Man challenged Thor to find out number of numbers between 1 to n, right? So we need to find out the number of numbers between 1 to n which are divisible by any of the prime numbers less than 20. So this is what we need to find out, right? So we need to write some code which will find out total number of numbers between 1 to n which are divisible by any of the prime numbers less than equal to 20, right? So this is what we are going to see. And in the input, you will be given the number of test cases t followed by t lines, one for each number n for each test case, right? So there are 5 test cases, and you need to find out the number of numbers which are less than 5 and which are divisible by prime numbers, right? Okay, so the only difference you will feel in this problem is that instead of just finding the numbers which are divisible by 2, 3 or 5, you need to find out all such numbers which are divisible by all primes less than 20, right? So we will compute what all primes are there, and now let us implement the same thing, right? Because logic is same, the logic is will remain same. Instead of taking 2, 3 and 5, you will take all prime numbers up to 20. So last prime number is going to be 19, right? So given an array of primes, you need to find out what all numbers are there which are less than n and which are divisible by these prime numbers, right? How many numbers are there, right, which are less than equal to n and are divisible by these numbers, right? So this is what you need to compute. Okay, so guys, I'm going to start with the coding part, and let's see, right? Okay, so let us start building our program, and I'm going to use long int, because when you are taking product of numbers, it can become large, and so I'm taking everything in a long, right? So first of all, we need to accept what all test cases are there, and then we also need to create a list of primes. So list of primes which are less than 20. So 2, 3, 5, 7, 11, 13 is there, 17 is there, and 19 is there, right? The next thing is for every test case, right? For every test case, I need to input what is the value of n. So let us define n and accept the n. And next thing is we need to yeah, create subsets, right? So one thing I'm going to define is up to what value I'm going to iterate, right? So you have 8 primes here, right? So number of primes you are going to have, so total number of subsets you are going to have would be 2 raised to the power 8, right? So total number of subsets are going to be 1 left shift 8. All right, and then because if you have n equals to 3, right? If you have if you had 3 numbers, we saw the total number of subsets are going from 1 to 7, and the total number of subsets are 2 raised to the power n minus 1, right? So these many subsets are there, and we are skipping 0, right? So I should also have a minus 1 here, right? Okay, so these many subsets I am going to have, and then I'm going to iterate over all the subsets. Okay, L equals to 1, I equals to 1, I less than equal to subsets, I plus plus. Okay, so what I'm doing here is I'm just going through these numbers, right? I'm going from these number, right? And if you write 1 left shift n, so it is same as 2 raised to the power n, right? So this is what I am doing here, and what I need to compute, I need to compute this product, right? I need to compute this product. So here I do not have any ABC, I have these numbers, these prime numbers 2, 3 and 5, right? So let's say this would be used in the denominator. So let us make one variable denominator which will be multiplied by these numbers, right? Okay, so let us say we have a variable denominator which is going to be equal to 1 ll, means long, and one more thing is I need to find out how many set bits are there, right? Because I need to see if that result that would be added to my result or that would be subtracted from my result, right? So what I'm going to do, I'm going to count set bits. So number of set bits, yeah, how many set bits you have, this is going to be equal to built-in pop count. So guys, this is a very useful method. It is an inbuilt method. It gives you, given a number I, how many set bits it has, right? And then I'm going to iterate over all the bits of that number, right? For some j equals to 0, j less than equal to 7, j plus plus, right? So why I'm doing is you can see, right? If you have 3 numbers, like in this case, right? In this case, you had only 3 numbers, but in my case I had 8 numbers, so I need to iterate over all the bit positions starting from 0 to 7. So I'm going to have 7 bit positions, right? And I'm going to see what bit is at a given position, and how do I check which bit is there. For example, if you have a number like this and I want to see what is the bit at this position, right? So what I will do, I will create one mask which looks something like this: 1 left shift 1, right? If you do 1 left shift 1, it is going to become 1 and 0. And if you do an AND, you will get a non-zero value, right? If this bit is 0, then you are going to get a 0 value, right? So if you get a non-zero result by doing um, number and mask, where mask is 1 left shift p, right, where p is the position you are talking about, right? So in my case, j denotes the position. So what I'm going to do, I'm going to do if I is my number, and I do 1 left shift j. Sorry, it would be a bitwise AND, right? So which means the corresponding bit is set. So you can say we are talking about the ith row here, and we are talking about the jth bit. Okay, so if this bit is set, I'm going to pick that prime number and multiply it with the denominator, right? So that I can make this product of abc, ab, ac, bc, and so on, right? So denominator is going to be denominator into primes of j. Okay, and then what I'm going to do, I'm going to see if number of set bits is odd. So and one basically tells me if the result is odd or even. Then I'm going to subtract n divided by denominator. Oh, I'm going to add n divided by denominator to my answer, else I'm going to subtract, which means number of set bits is even. All right, and few more things which we need to do here is we need to define what is the answer in the beginning. So let us say ll answer equals to 0, and number of subsets we have already defined. Anything else we are left with? I think that should be good. So let us try to print the answer, right? So cout answer endl and return 0. All right, so let us get the test cases and check, right? So we are getting 4, 9, 11, 14, and 148. Okay, 4, 9, 11, 14, and 17. So minor mistake in the code. Okay, 183 was not there, right? So I think input is wrong. So last input was 18, I guess. Yeah, 18 it was, right? So input is, so output is 4, 9, 11, 14, and 17, which matches our with the output. So now let us try to submit our code. And if you have any confusion, I will just go through it once more and let us see, right? So yeah, we got a correct answer, and so this is how we have solved this problem. And now if you have any confusion, I will just go through the code once more so that you guys are able to uh, clear your doubts, right? So guys, what we did is we iterated over everything, right? We first figured out how many subsets of 8 numbers can be there, right? So we have 8 prime numbers, so we can make how many subsets? 2 raised to the power 8 minus 1 subsets, because we are not talking about the null subset, right? So this is what the number of subsets are, right? And then I started iterating over all the subsets starting from 1 to 2 raised to the power 8 minus 1, and for every number I have a corresponding number in binary, which is going to have at most 8 set bits, right? So I iterate over what all 8 set bits are, and here I have a list of primes, right? So I have a list of primes starting from 2, 3, 5 up to 19, right? So 19 is my 8th prime, right? Then I see if this bit is 1, which means I'm just going to take 19 and I'm going to multiply my denominator with 19. So I will find out how many numbers are divisible by 19 by doing n divided by 19, right? And I see how many set bits are there in this number. So there is only one set bit. So this term will be my added to my answer, right? Maybe next time I go to some number 5 which has 1001. So this will correspond to 19. So denominator will become 19. Then I skip this prime number, so 17 is skipped. I take prime number which is 13, right? So 19 into 13 will be there, and n divided by 19 into 13 I'm going to do. And since the number of terms I'm combining here are 2, so I will subtract this from my answer. And for this number you will find that all the set bits, all the 8 set bits are 1. So you will just multiply all the prime numbers. That would be a huge number, and that is the reason I'm taking denominator as long, right? So this is what we have done in this tutorial, and I hope you liked it, right?